Hey guys, it's Miss Johnson here, and I'm here to bring you your notes for section 9, 4, and 5, which is on common logs and natural logs. Up at the top of your page, we're going to just start by looking at our calculator for a second. Up to this point, we haven't done a whole lot on our calculator with logarithms, but if you take a look at your calculator, there is a button that says log. You should find a log button. If you're looking at the TI graphing calculators like a TI-83 or 84, you should see it next to the 7 over on the left-hand side. If you're using a scientific or an iPad calculator or something else, you'll find it in a different spot, but there is an actual logarithm button. We're going to talk about what that button does for us today. Let's just start by looking at how we plug it in. We would plug in the log of 3. I'd hit the log button, I'd hit the 3 and hit enter, and I want to round it to the 4th decimal place, and in this case that would give me approximately 0.4771. If I did the log of 0.2 and plugged that in, I'd have approximately negative 0.6990 after rounding. Now these are called common logs. If you notice up in the question, they don't have a base showing. We've seen bases so far in all of our question. Well, that's because for common logs, if the base is not shown, it's a base of 10. Base 10 logarithms are common logs. It's kind of like having a radical sign with no index showing. If we had a radical sign with no index showing, we know that the index is 2. Same thing here. If I'm taking the log of, let's say, 6, and there's no index showing, that means my index is 10. So base 10 are our common logs. Now let's talk about how we could use those to solve exponential equations. Now just think about 3 to the x power equaling 27. This isn't an example on your notes page, but let's just think back to what we would do here. In the past, we don't know how to take the xth root of something that doesn't exist. We can't do that because we don't know what x is. But we might ask ourselves 3 to what power equals 27? Okay, well I could check on my calculator, 3 to the first, 3 to the second, 3 to the third, and go on and on. I would see that 3 to the third power equals 27, which would mean that x has to equal 3. All right, that works when I have a root and a number that are even, that I can plug that into. But what happens when we have something like 3 to the x power equals 11? There's no whole number that when I take 3 to that power, I get 11. So what I have to do is use logs to solve for that. So that's what I'm going to do here. I'm going to take the log of both sides. I'm going to take the log of 3 to the x and the log of 11. Since I'm taking the log of both sides and I'm using common logs here, I know that the base is 10 for both. So I can use this to solve what I need to find, solve for x. Think back to the properties that we learned yesterday. We know that when we have 3 to the x power, I can take that x and bring it out front of the log. So I'd have x times the log of 3 equaling the log of 11. Well, now I want that x alone, so I'm going to go ahead and divide by the log of 3. And that's what you plug into your calculator. Plug in the log of 11. Make sure you put that in parentheses, just in case your calculator wants to string some things together. Log of 11 divided by log of 3. And the values that you should get here, you get about 1.0414 for the log of 11 and about 0.4770 for the log of 3. And when I divide those two, I get 2.1827. So that's the approximation for x in this example. Same thing in number 4. Now I'm looking at 6 to the x power is equal to 42. So I can't take the x root of something. I don't know how to do that. So I'm going to take the log of both sides and get that x out of the power position. So I have the log of 6 to the x equaling 42. Oops, sorry, log of 42. Make sure I put that in. And that means I can take that x and bring it out front, and that gets it out of the power position, which is what I'm trying to do, so that I can solve for the remaining value. I divide by the log of 6 so that x is alone, and I have x is equal to, in this case, the log of 42 was about 1.6232. The log of 6 was about 0.7782. So I get x is approximately 2.086. So that's my x value in this case. So what we've learned here, or what you've seen an example of, a couple examples of, it says if both sides of an exponential equation cannot easily be written as powers of the same base, You can solve them using the logarithms. You can solve by taking the log of both sides. So that's what we do. Let's move on and talk about natural logs for a second. Natural logs are the ones that have a natural base. They have a base of e. Okay, they have a base of e there. This ends up giving me a value. I have a value for e. E is also known as a value of 2.71828, so you'll see that, okay? The inverse of y equals e to the x, which is a natural base exponential, would be the natural log of the function. So here, I've got the function y equals e to the x. The inverse of that would be the natural log of x. And this ln tells you that it's a natural log. That's our notation there. Okay, it's the log of the natural base. So if I take a look at number 5, it says write an equivalent exponential or logarithmic equation. So in part A, I have e to the x is equal to 5. That's an exponential equation. And I want to turn that into a log equation. In the past, what we've learned is that we take the base and raise it to the power, and it equals that. So I'd have e to the, I'd have the log base e of, here we go, log base e of 5 is equal to x. Well, in this case now, I know that the log base e has its own notation, which is ln. So ln of 5 is equal to x. And when you put that ln in there, you know that you're looking at a base of e, and you don't need to write the base of e. If I look at part B, I have the natural log of x is approximately 0.6931. So that means I have the log base e of x, so I would have e raised to that power. E raised to the 0.6931 is approximately x, and that's my logarithmic form for that. The base is e, and the power is 0.6931. Okay. So let's just do a couple examples of solving using natural logs. In number 6, it says 5 times e to the negative x minus 7 is equal to 2. So I am going to start by, where'd my number 6 go? There it is. I'm going to start by solving just like I normally would. I'd have to add that constant over to get rid of that. I got to get rid of everything except for the base of e, the power. So I'm going to add 7, and that gives me 5 times e to the negative x power is equal to 9. Then to get rid of that 5, I'd divide by 5. So I'd have e to the negative x power is equal to 9/5. And you can just keep it as 9/5, that's fine. And now I want that power to come outside. Since I know that the base is e, that means I'm going to be taking the natural log. So I'm going to take the natural log of both sides. And what that does is that takes my power and moves it out front. So I have negative x times the natural log of e is equal to the natural log of 9/5. Now here's the beauty. When I look at the natural log of e, the natural log of e is actually 1. So this natural log of e goes away because the value is 1, and that's a note that you could write down for yourself. The natural log of e is going to give me 1, because what that is a base of e raised to the first power gives me e, and we all know that that's true. E to the first power, anything to the first power is itself. So by taking the natural log of both sides, I've gotten rid of that logarithm. I have negative x is equal to ln of 9/5. I can go ahead and plug that into my calculator. The natural log of 9/5 is about 0.5877, so I'd have negative x is equal to 0.5877, and then I need that to be positive, so I'm going to divide by -1. X is about -0.5877. So there is the solution to one of the equations that I'm looking at today using natural logs. I'm going to go ahead and quit our video there today, and we'll pick up with the rest of our notes tomorrow in class. Thanks for watching. Don't forget to go back and do your quiz on Schoology. Have a good night.